Hello all, let us have a look at Tishchenko reaction. So basically, this reaction leads to an ester from an aldehyde. 2 moles of aldehyde reacts to form 1 mole of ester in presence of Lewis acid. Now, what is the mechanism here? So the aldehyde reacts with the Lewis acid. So how does this react? So aluminum is a Lewis acid and it has the capacity to accept electron pair. Oxygen has 2 lone pairs. We have shown 2 electrons here, that's 1 lone pair, and this will donate electrons to aluminum. So let's show that with a curved arrow like that. What does this arrow mean? This means these 2 electrons are going to stay in between this oxygen and this aluminum. Or in other words, the maximum probability of finding these electrons is going to be in between this oxygen and this aluminum. Or in other words, there is going to be a new bond between oxygen and aluminum. Okay, let's draw that. So that's the new bond. Now, the 2 electrons in this bond belong to oxygen, like here. Okay. Now, once in a bond, to calculate charges, we have to consider 1 electron belongs to this atom and the other electron belongs to this atom. In a bond, 1 electron belongs to one atom and the other electron belongs to the other atom. Both this electron is from oxygen, but now 1 electron belongs to aluminum. So aluminum got an extra electron. So aluminum will have a negative charge. When a neutral species gets an electron, it will have a negative charge, as there are no nuclear reaction, obviously. So now how about this oxygen? Both these electrons belong to this oxygen. Now one of the electron belong to oxygen and one belong to aluminum. So oxygen lost one of its electrons. So oxygen will have a positive charge. So we wrote those charges there. Now what happens? Now this oxygen is more positive, and which in turn makes this carbon, this carbonyl carbon, even more positive. So it was already a little bit positive center. Even before this aluminum coordinating on this oxygen, there was a shift of electron towards oxygen in these bonds because oxygen is more electronegative. But once aluminum bonds here, oxygen will have a full positive charge, which means oxygen will pull these electrons even more effectively. So the electron density will be reduced even more in this carbon. So electron density around this carbon will reduce even more, which means this center, this carbon, can be considered as a positive center. So like this, a shift of electrons towards oxygen is happening. This arrow means the full shift of electrons to oxygen, which will caused by an attack of another nucleophile or a negative center. So let's, okay, like this, but this attack is coming from nothing but another molecule of the same aldehyde. So let's show it like that. So what does these arrows mean? This arrow means that these 2 electrons are going to stay in between this oxygen and this carbon. Or in other words, maximum probability of finding these electrons is going to be in between this oxygen and this carbon. So let's draw that bond. Now, as this bond is forming here, that is, this bond is forming, an old bond has to break. Otherwise, there will be 5 bonds on this carbon. As this new bond is forming, an old bond has to break. This pi bond is the one breaking, and it will break like that. So let's look at this oxygen. This oxygen was neutral. The 2 electrons on this oxygen is now in between this oxygen and this carbon. Once in a bond, we will say 1 electron belongs to this carbon and 1 electron belongs to this oxygen. Now oxygen lost one of its electron, so oxygen will have a positive charge. So we have shown that here. Now look at this bond. One electron belongs to this oxygen, one electron belongs to carbon. Both the electron went to oxygen. Now both electrons are in the vicinity of oxygen. Actually, one electron belonged to this carbon. So this carbon lost one of its electron. In other words, oxygen gained one extra electron. So oxygen had already a positive charge. Now it becomes neutral. When a positively charged species gets an extra electron, it will become neutral. Aluminum remains as a negative charge species or 8 complex. Just like we saw in the previous structure, this oxygen is positive now. That means these electrons are pulled towards oxygen more effectively, and this positive center, this carbon, becomes even more electron deficient, which leads to a hydride shift. Now these two electrons is going to stay in between this hydrogen and this carbon. As this bond breaks, there will be a new bond between this oxygen and carbon at the cost of this oxygen aluminum bond. So let us draw that too. Okay, this is the curved arrow showing these two electrons are going to stay in between this oxygen and this carbon. That means there's going to be a new bond between this oxygen and this carbon. That means a pi bond. This whole thing becomes a double bond, and this hydrogen will shift from there to here. Now there's going to be a new bond to this carbon, obviously with this hydrogen, but as there is a new bond, the old bond has to break. As the carbon is already 4 bonds attached to it, a new bond means a 5th bond. That will not happen. So as the new bond forms here, an old bond, that means the pi bond, will break, and both electrons in this pi bond is going to stay on this oxygen. So let us copy the whole structure and draw the bonds there. So this arrow means these two electrons are going to stay in between this oxygen and this carbon, which means this bond is no longer there, and it's automatically showing a hydrogen, which is wrong. As aluminum lost one of its electron, and it will become neutral, and this hydrogen as a hydride ion shift towards here. So this bond breaks and a new bond forms from here. Okay, now as this bond forms, an old bond will break and both electron will go to oxygen. As both electron goes to oxygen, oxygen will not have this positive charge. Oxygen becomes neutral. So what is this species? This is actually our ester. So our Lewis acid got regenerated. So let's take it aside and let's look at this structure. Before that, let's draw the arrow. So what is this species? This is an ester. Okay, so this is our ester. Actually, this alkoxide could now be coordinated to our ester, but if there is an aldehyde molecule left, this aluminum will coordinate with that, and again the reaction will happen. So this aluminum alkoxide will still be coordinated with this oxygen, but if there is an aldehyde, it will get transferred to that aldehyde. Whole reaction will happen again. So once the reaction over, you can wash it with water. So this alkoxide will not be there. Get the ester back. So let's go over once again. This Lewis acid reacts with our aldehyde and becomes a positive center, and aluminum becomes a negative center, an 8 complex, and now this carbon becomes even more positive, and because of that another molecule of the same aldehyde will attack this carbon, and a new bond between this oxygen and the carbon, and this old bond will break and this positive charge will disappear. Now as this new because of this new bond, a positive charge will be on this oxygen. Just like in the earlier case, this carbon becomes even more positive, and which leads to a hydride shift from this carbon to this carbon. That is 1, 2, 3 atoms apart. So it's a 1,3 hydride shift. So because of a 1,3 hydride shift, you will get an ester, and ester might be coordinated with the aluminum, but once you add water, you will get your ester without any coordination from Lewis acid. Similarly, we can have a reaction, a same kind of reaction when we add sodium methoxide or a base like that. So we saw a reaction with the aluminum alkoxide, but it can happen with the sodium alkoxide or potassium alkoxide, alkali metal alkoxide. What I was trying to say is, actually Claisen was the one studied this reaction first or reported this reaction first. But Tishchenko is the one. Tishchenko was working on aluminum alkoxide, and he came to he happened to develop this reaction further. So the name Tishchenko reaction. But the first reaction was using another alkoxide, simply sodium alkoxide or potassium alkoxide, or alkaline metals, metal alkoxide can also do this reaction. So now sodium ethoxide is not a Lewis acid, as you know. So how does it do? So there is a slight change in the mechanism, but the reaction, the product can form. The same thing can happen. I mean, the same from the same starting material, same product can be obtained using sodium alkoxide or potassium alkoxide like that. And let's try to find that's Claysen's version of this reaction. But that's not, I mean, this one is more efficient, but still as a historical standpoint and also mechanistically, it's a bit more interesting. How does it work with alkoxide? So let's try to explore that also. പ്രോഡക്റ്റ് നോക്കുമ്പോൾ അങ്ങോട്ട് ശരിയാവുന്നില്ല, എന്താ സംഭവിച്ചത്? So now what should happen to get our ester? So the mechanism goes like this. This bond comes back, and the hydride shift happens here. There is hydrogen here. We didn't write it, so let's write that hydrogen there. We need it now. That's what happens. Okay, so hydride attacks this carbon, and this OR dash gets eliminated like that, right? So let's copy the whole thing, try to make sense of it, sense of the curved arrows. Okay, let's place it somewhere here. Okay, now this means a new bond is forming here. That means this bond. An old bond is breaking. That means this bond is breaking. Obviously, 5 bonds to this hydrogen, that will not happen. This breaks apart, and that new bond is between this carbon and this hydrogen. This bond breaks. Now there's 5 bonds to this carbon. That will not happen. Before that itself, this bond breaks apart and OR minus leaves. OR minus leaves. Now we have our ester. So this is our ester. Let's try to make it a bit more beautiful. So we got our ester. So through this mechanism also. there are two mechanisms for this Tishchenko reaction. So the first one is using aluminum alkoxide. Aluminum alkoxide, that is actually the method, the go-to method of Tishchenko reaction. Most of the people will list this as the Tishchenko reaction. Actually, there are some papers in which this one also is also mentioned. This Claisen version. So this is the older version, but not that effective. But Tishchenko made it better. See the whole picture now. So this aluminum alkoxide method is the actual method. That's the real Tishchenko reaction, let's say. But this one is also there. This is the actual first report of this Claisen reported the same conversion, and we can write this mechanism also. So both mechanisms are possible. These two attributes, this is same. Means in both this mechanism, this disproportionation is happening. 1,3 hydrate shift is happening, and only thing is Lewis, this reagent is different. In this case, you are making this one aldehyde even more reactive, while in the other case, we are you are making this oxygen even more reactive. Right. In one case, Lewis acid attacks here and makes the other aldehyde to attack this carbonyl group, making this the carbon even more electropositive, or this carbon. So that's this step. But in the Claisen reaction, an OR dash minus attacks in this carbon first and forms an O minus, and this O minus attacks this carbonyl group. See the difference. So that's the difference there. Okay. Hope you understood this Tishchenko reaction.